part 1 of the videos on bonding involved ionic bonding, generally between a positively charged cation that's metal and a negatively charged anion that is a nonmetal. Today we're going to look at covalent bonding, which is the sharing of electrons between two nonmetals. So again, remember the nonmetals on the periodic table appear on the right side of the periodic table, on the right side. So we're looking at these as being considered the nonmetals on the periodic table. We're mostly going to be looking at this top row, so carbon, nitrogen, oxygen, fluorine, and then the halogen column. They're going to be the most common of the elements that we'll look at with covalent bonding. So unlike ionic bonding, which involves the transfer of electrons, covalent bonding involves the sharing of electrons. Remember, that's the symbol for electrons, between two or more atoms. So rather than transfer electrons to obtain a full valence shell, this time we're going to share the electrons to achieve the full valence shell. If you don't remember the definition of valence shell, I'd encourage you to check the ionic bonding video out first when I walk through those definitions with the ionic bonding. But as a quick reminder, the valence shell is the outermost electron shell where all of the bonding takes place. The electrons in the valence shell are the only electrons that are involved in bonding. The inner core electrons are not going to be involved in that bonding. Like with the ionic, I think the best way to demonstrate covalent bonding is to do so with an example. And we'll go 2 examples here of the covalent bonding, and then we'll look at a third one that kind of combines the 2 first examples that we look at. So first one, we'll look at the molecule methane. And notice I use the word molecule here because molecules are specifically compounds that are made up of covalent bonds. That's the definition of a molecule, one that's made up of covalent bonds. So we have carbon and 4 hydrogens. I will first draw the carbon here. You have the inner electrons. Remember that first shell can only have 2. And then the second valence shell, I'm going to switch to green electrons here to make them easier to see. We have 4 valence electrons. Because if you go back, we don't include the transition metals. We have column 1, 2, 3, 4. So that means carbon has 4 valence electrons. Hydrogens. We got 4 hydrogens. I'm going to use orange as the electrons for hydrogen. Each has 1 electron. What they're going to do here is share these electrons. Sharing is caring, right? They're going to share these electrons in order for all of the atoms to achieve a full outer shell. If I count up all of the electrons, each hydrogen has 2 electrons, one from itself initially and one from the carbon that is being shared. So that gives it 2 electrons in the valence shell, so it now has a full outer shell, since that initial electron shell, remember, can only have 2 electrons. Carbon has 4 of its own electrons, and then each hydrogen shares one of its only electron with the carbon. So add those all together, we get 2, 4, 6, 8 electrons, and a full outer shell. Now we can draw this in line structure as C with 4 H's. This line here represents a single bond. And a single bond is 2 electrons, right? 1 electron, 2 electrons in a single bond. Not all bonds are single though. In the next example we'll look at, we'll have what's called now a double bond. So the next molecule that we're going to look at to demonstrate a double bond is carbon dioxide, CO2. I'll start off again with carbon in the middle. Draw the inner electrons. And then now, I can do a better circle than that. The outer electrons, I'll represent those with red because they're the valence electrons. Now I have 2 oxygens. I'm going to put the X there too so we don't think that that's a circle. So oxygen, inner shell, and then second shell. I'll use blue here. So we have 1, 2, 3, 4, 5, 6. Oxygen over here. 2 inner electrons. 1, 2, 3, 4, 5, 6. Where am I getting 6 from? It's in column number 6. 1, 2, 3, 4, 5, 6. Other way to remember, oxygen is atomic number 8, which means it has 8 protons and 8 electrons in elemental form. There are 2 electrons in the inner shell, meaning there has to be 6 in the outer shell to add up to 8. The only thing I'm going to do here to change my drawing is I'm going to move, I'm not switching electron shells here, but I'm going to just move where in the electron shell you find the electron. Because in reality, the electron shell is 3-dimensional and the electrons are constantly moving around it. So carbon needs to get 4 more electrons from the 2 oxygens total to be able to get 8 in the outer shell. So how they'll do that is oxygen, rather than sharing 1 electron, like hydrogen did back here, shared 1 electron with carbon, oxygen will share 2 electrons with carbon. And this oxygen will share 2 electrons with carbon. So now, if you add up the number of electrons on the left oxygen, it's 1, 2, 3, 4, 5, 6, 7, 8. If I add up the number of electrons on this carbon, 1, 2, 3, 4, 5, 6, 7, and 8. Oh, I see why I got confused here. Okay, give me 1 sec. When I went back to delete some of what I drew, the old electrons appeared again that I had moved, right? So these ones aren't here. Yeah, that threw me off for a sec. So good job if you caught that. I have the 1 double bond here and the 1 here, so when I add these up, it's 1, 2, 3, 4, 5, 6, 7, and 8. We'll pretend that was a little test there to see if you're paying attention. You're probably like, wait, how did carbon get 2 more electrons than it should have? So if you noticed that, great job. So again, carbon starts off with 4 valence electrons. Those are the red ones. So it needs to get 4 more through sharing. So it gets 2 from the oxygen on the left and 2 from the oxygen on the right. And likewise, the oxygen on the right has 6 of its own valence electrons, plus the 2 red ones from carbon to give it 8 total. So now the line structure for this, rather than drawing a single line, it's going to be a double line, kind of like an equal sign, and that indicates a double bond. That will give you your carbon dioxide. Lastly, I'll go over one more example that will have both a single bond and a double bond in it. So it'll be both of the bonds that we've looked at. So for this example, we'll look at the molecule formaldehyde. Which is CH2O. So carbon down here, inner shell, 4 valence electrons. 1, 2, 3, 4. Hydrogen will draw in next. Hydrogen has just 1 valence electron. And then oxygen has 2 in the inner shell and then 6 in the outer shell. All right, let's see if you can try to guess what's going to happen here. So we'll form a single bond when this hydrogen shares its electron with the carbon, and that carbon shares its valence electron with the hydrogen. That forms a single bond. Over here, we'll form a single bond as well. Now, a little trick that you can use, hydrogen will never form anything but a single bond. It only has 1 electron to share. It cannot share 2 electrons, so it can't form a double bond. So if you're ever unsure, hydrogen can never form a double bond or a triple bond. Carbon, on the other hand, and oxygen both can, as we've already seen in the example. So now, if we add it up, carbon has 1, 2, 3, 4, 5, 6 valence electrons. So it needs 2 more. And it will get those 2 more from the oxygen. So now carbon has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. And the oxygen has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So it has filled its outer shell. Each hydrogen has 1, 2 valence electrons. 1, 2 valence electrons. So all the atoms are happy. They have filled their outer shell. So the line structure of this would be carbon double bonded to an oxygen and single bonded to 2 hydrogens. Hint number 2. Carbon always has 4 total bonds. Here we have 2 single bonds, so you can think that as 2 times 1 plus 1 double bond. 1 times 2, that's just 2 plus 2, and 4. So carbon will always form 4 bonds. All right, I know we've looked at 3 examples. One more thing to talk about with covalent bonds. Polar versus nonpolar covalent bonds. So what polar and nonpolar refer to is, are the electrons shared equally between the 2 atoms? So we'll start with nonpolar. So nonpolar, the electrons are shared equally between atoms. Easy examples of this would be diatomic molecules. Cl2, O2, N2, H2, right? It's the same exact atom, so of course they're going to share equally between them. The more tricky one to look at is polar, which means the electrons are shared unequally between atoms. Pen stopped working there for a sec. To fully understand polar, we have to look at a term and go back to the periodic table. So the term we're going to look at here is something called electronegativity. It kind of is what it sounds like. It's an atom's attraction to electrons. So remember, an atom has protons in it that are positively charged, and then the negatively charged electrons. And positive and negative attract each other. As I move across the periodic table, I increase the number of protons as I move up atomic numbers. So let's look specifically at row number 2 here. Lithium has 3 protons. Beryllium has 4. Boron 5. Carbon 6. Nitrogen 7. Oxygen 8. Fluorine 9. So every time I go across, I add 1 proton. I also add an electron, of course, but I don't add an electron shell. So I'm just going to put an A here to represent the atom. It's filled in its first shell. Lithium has 1 valence electron. Beryllium has 2. Boron 3. Carbon 4. Nitrogen 5. Oxygen 6. Fluorine 7. So notice, I'm continually adding an electron, but it's staying in the same shell. So it's staying the same distance, technically, nucleus. But every time I add a proton, that's more positive charge, that's more attraction of those electrons towards the nucleus. So as I move across a row, the electron becomes more and more attracted to the nucleus, and the nucleus has more of a pull on those electrons. It has higher electronegativity. So the atoms with the highest electronegativity are oxygen, fluorine, and nitrogen. They have the highest electronegativity. So if you have a compound with, say, hydrogen and oxygen like water, this would be polar. And the way I draw this is I'd have oxygen, and then here I'll draw in the electrons in the bond between the oxygen and the hydrogen. The oxygen would have more of an attraction for those electrons, so I draw something that looks like this. There's a slight positive charge on the hydrogen, and then there's a slight negative charge on the oxygen. NH3 would be polar, because nitrogen would have more of an attraction. NO2 would be polar, because oxygen would have more of an attraction for those electrons. Cyanide, Cn- would be polar. The other important bond to note is a carbon-hydrogen bond is nonpolar. Their electronegativities are so similar that there's not an unequal sharing of the electrons between them. If you still have some confusion with polar and nonpolar, that's fine. In the video on the properties of water, we'll discuss polarity more with the water molecule, and hopefully that gives you a better understanding of polarity in general. See you next time.